Hello, Mr. Leacher. My name is Omar Gonzales, and I'm here to talk about the Huffman coding algorithm. Let's talk about the history first. There was an unsolved problem to find the most efficient binary code. David Huffman was a PhD student at MIT in 1951. His professor gave him the choices of a final exam or solve this problem. Huffman decided to take this challenge, but he was unable to, to find the most efficient binary code at the beginning. When he was about to give up and starting for his final, he came up with the idea of using a frequency sorted binary tree which solved the problem. What is this algorithm? It's a lossless data compression algorithm, meaning that no data or information is lost after all the data has been compressed. This compression method reduces the input uh, for about 10 to 30% of the original size. There are many common compression formats such as JPEG, PNG, MP3, and gzips that use the Huffman coding method. The main advantage of a compression algorithm is that it reduces the amount of bits needed to save data storage and, and the bandwidth needed for data transfer. Okay, let's talk about the description of the algorithm. Basically assigns variable length codes instead of fixed length codes to encode characters. The length of the assigned codes are based on the frequency of corresponding characters. In other words, characters with higher frequency will have shorter codes and characters with shorter frequency will have longer codes. Also, a frequency sorted binary tree is implemented to store the characters. Lastly, a left traversal that has the value of zeros and a right traversal that has the value of ones is implemented within the binary tree. To build the tree, we start from the bottom up instead of the top down. A priority queue where the node the lowest frequency is given highest priority for the tree. Here is the algorithm, an outline of the algorithm. Create a leaf node for each symbol and add it to the priority queue, in this case a tree. While there is no more nodes, there is more than one node in the queue, remove the two nodes of the highest priority or lowest frequency from the queue. Create a new internal node with these two nodes as children and with frequency equal to the sum of the two nodes' frequencies. Add the new node to the queue. The remaining node is the root node and the tree is complete. Okay, I will explain now with an example. I think this is going to be easier this way. Here we have an input that uses 221 bits. It's before the compression. There are 7 characters. The characters are displayed on the left. Their fixed length code is 3-bit code, and their frequency are on the frequency columns, and the total bits is obtained by multiplying the 3-bit code by the frequency. Now the input has been sorted in non-decreasing order by frequency. That's why the characters with lower frequency are on the top, such as new line, C, and at the bottom are the characters with higher frequencies, such as E, A, F. Okay, and if we sum up the total bits, it will give us 200 251 bits before compression again. Okay, now I will open my research paper. That's where I have the tree, the Huffing tree, and we will go over. I want to keep this table open so you can follow me. Okay, we're gonna take first the two characters with the lowest frequency. In this case, is new line and C. We're gonna unify them by creating a parent node. This parent node we have the value that the sum. The parent node's value is the sum of both frequencies. In this case is 1 and 3, 4, as you can see it. Now we're gonna take the next character with a lowest frequency. In this case is B. So we're going to cross it out, and we're going to add this node or character to the tree by creating a new parent node that has the sum of both frequencies. 4 and 8 is 12. Okay, we're going to do this again, and with the next one is D, frequency 10. Right here 10, 12, and then it's 22. It's been added to the tree. Sorry. And here we have the next one, which is the next one is F, 18 and 8. These two are lower than the current parent node, which is 22. So we're going to create a subtree here. We're gonna create an independent subtree. We're gonna cross them out. We're gonna add it here. And now we have 27 left, which is added to the tree with a lower parent node. In this case 22. So we added here 20 the 27 to this tree on the right, and the new parent node is 49. So this will give us, and then we have to merge both substrate to a 1. It will give us 2 here, whole tree. After that we have to put ones on the left and zeros. Zeros on the left and ones on the right for the edges. I will give you here the presentation. Here is a complete Huffing tree. Okay, you can see zeros and ones, and the characters and the frequency with their new variable length codes. Here, after Huffing coding compression, the input uses now 210 bits. This is a big improvement over the previous size, which in this case was 251. Now we have 210 bits. Is 20% less. And like I said at the beginning, characters with higher frequency like A and E has shorter uh, codes, only 2 bits, and characters with lower frequency such as C and new line have longer codes, 5 bits in this case. Okay, now let's talk about time and space complexity. Like I said at the beginning, priority queue will be needed to store the characters. We're going to store each character with a node, and the insertions take a node insertion takes big O log n. There are 2 times n minus 1 nodes in the Huffing tree. Therefore, the time complexity is big O n times log n. And we gotta make a note here that the time is not important because n is the number of symbols and characters in the alphabet. Therefore, n is going to be a small number. Okay, the same thing for the space complexity. That the tree should be the space needed to build the tree should be theta 2 times n minus 1, or theta n. Okay, it's a very important algorithm that applies to different file formats. And this concludes my presentation. Thank you very much.